Welcome to my YouTube channel. Today we're going to look at the galvanic cell, which is the voltaic cell. Guys, please excuse me about the sound. The background sound is the rain and it's windy outside. Right. The galvanic cell, we see it by two bakers. We call it its half cells. It has two bakers and it has the cell bridge. It has two electrodes, and these two electrodes are active electrodes, which is they take part in the redox. We have the external circuit, which is we have that connecting wire that has the voltmeter, right? And we have electrolytes here, and we have zinc electrode with the zinc sulfate electrolyte, copper electrode with the copper electrolyte sulfate. Let's zoom in the galvanic cell. Let's look at the galvanic cell, the energy conversion. The energy conversion of the galvanic cell is from chemical energy to electrical energy, right? And then let's look at the spontaneity of the cell. The cell is spontaneous. It's spontaneous. What do we mean it's spontaneous? We mean that it occurs on its own. On its own, it does not need, no need for power supply. No need for power supply like the battery. It doesn't need battery, right? And then the E cell, or the EMF that is produced or induced here, it is greater than zero, or it's positive. Always it will be positive because it's spontaneous, right? And another thing that is important about the galvanic, it has the soul bridge. And the soul bridge, what does it do? It maintains the electrical neutrality and it completes the cell, right? Now another thing that is important here, the electrical current. The electrical current, which is the electrons, they move from the anode, to the cathode, right? We can say A to C, A for anode and C for cathode. Sorry. And in the soul bridge, the N ions. Okay, I'm gonna talk about that. Let's leave that. Now, guys, here we have a zinc copper cell. So between the zinc and the copper, we would like to know which one is oxidizing and which one is reducing, right? We're going to look at the standard reduction potential table. Here's the standard reduction potential table, guys. I use a 4B. This is 4B, right? It's table 4B, this one. So I'm not using A. Right, now let's underline the zinc. Here's the zinc. And where's copper? Be mindful, guys, we're going to use this copper, this one that I'm underlining, the copper with the two electrons and with the two charges, with the 2+ charge. Guys, the one that is the half cells, these are the half cells, guys. All of these are the half cell reaction. So when they talk about write down the half cell reaction, this table is useful. So in these half cells, guys, as we can see here, they have double arrows. The double arrows, that means it's reversible. But when you write the half cell, we write it in one arrow. So when we look at the oxidation, the oxidation is going to be the reaction that is on top. So it means in this case, the zinc is going to lose electron as oxidizing. And when we look at the reaction, we're looking at it from right to left. And that's the oxidation. And then the one that is at the bottom, which is the copper electrode is going to reduce. So we look at the reaction from left to right that way. So this one is undergoing the reduction, right? Is undergoing the reduction. And guys, when we write the half reactions here, let's look at the zinc. Since it's oxidizing, you start with the zinc atom and then arrow and then zinc ion and the 2 electrons, just like this. You say zinc and then arrow and then zinc 2 plus and the 2 electrons that it has lost. That's how you write that. Now let's look at the oxidation. The oxidation, you write it as it is written there, but without the double arrow there. You need to write with the single arrow. So it's going to be what? Cu2 plus ion with the 2 electrons that it gains. And then now it has gained electrons. It's a solid, right? That's how you write it. Do you see? It's exactly the same as this, but you just will write one arrow that is going forward, right? And all the arrows needs to be forward. Remember this one, we start with this and then the forward arrow and then this. So you write it that way, right? Guys, if you look here, there is a diagonal line that you can write from the tail of these arrows that I've written there. That diagonal line, guys, it's a positive gradient mathematically. So my gradient is positive. Gradient is positive. So if the gradient is positive, that means the reaction between the copper and the zinc, it's spontaneous. It's spontaneous. Remember, I said in the spontaneous reaction, the E cell or the EMF is greater than 0 or it's positive. So the voltage that is induced between the two is positive. So here the voltage is the voltage of the zinc, and here's the voltage of the copper. So guys, here, and here's another thing to memorize this. So it will be this way is reduction, and then up, and then up, and then this way it's going to be what? Oxidation. And that diagonal line there, it means spontaneous, right? It's a spontaneous reaction, right? Another thing, guys, when they talk, if you look at these arrows, there are arrows here. If you look at these arrows that are going down, and this arrow that is going down, and you have an arrow that is going up. So this arrow, it says here, increasing in oxidizing ability. We know the oxidizing agent. The oxidizing agent is the one that loses the ones that gains electrons. So when always they talk about answer your question, refer to the relative strength of oxidizing ability. That means that the oxidizing ability in table 4a, it increases from top to bottom, right? So between the zinc and the copper, you're going to look at these two, right? The oxidizing ability, they refer to these ones, all of these, right? All of these ions. So it's going to be this and that, right? So let's zoom on it. So let's look at the zinc. The zinc, since it's on top, the zinc ion, since it's on top of the copper ion, right? The zinc, since it's on top of the copper ion, so we will say it's a weaker, because it's a weaker oxidizing agent. Oxidizing agent, right? When you compare to copper ion. Let's look at the copper ion. The copper ion, since it's at the bottom and from top to bottom, there's an increase in oxidizing ability. We'll say it's a stronger oxidizing agent than zinc, right? So guys, if you look at this side again, there's an arrow this side on the right hand side that is going up. It says increasing and reducing ability. The reducing ability is the one that loses the electrons. So the one that loses electron is going to be this, right? And yeah, so that means when we talk about the reducing ability, we are referring to these ones, right? So whenever you explain about the reducing ability, we're going to refer to those ones. So guys, we're going to look between copper atom and the zinc atom. So since the strength is increasing from bottom to top, so zinc is a stronger reducing agent than copper, and copper is a weaker reducing agent, right? I hope that makes sense, guys. Let's go back to our galvanic. And another thing that was important in the galvanic cell, guys, it's an exothermic reaction. It's an exothermic reaction. Our delta H is going to be less than 0. So the galvanic reaction, it's an exothermic reaction all the time. There's more energy released than absorbed, right? Because it releases energy, doesn't take energy, right? So we have seen, guys, here that the zinc is an anode, it's oxidizing. So this is an anode, and the anode is what? Is negative. And then we've seen that the copper is a cathode because it's reduced. There's a reduction that occurs. It's going to be what? Positive, right? It's very important, guys. And another thing that is important, the E theta, which is the voltage of zinc, is going to be a small value compare to the copper value. The voltage of the copper, since it's reduced, which is since it's gaining electrons, it's going to be a greater value. It's going to be a greater value or a bigger value. Let's go in and double check that. So look at the value of the one that oxidizes. It's negative 0.76, and look at the copper, it's 0.34. This one is smaller. In oxidation, always it's going to be a smaller value, and the reduction is going to be a bigger value, right? And another thing that is important, the manomagnetic way, or the technique to remember what is happening in an anode. You use the word, it says N-ox. The N-ox, that means the oxidation occurs. In an anode, oxidation occurs. And another one will say in the cathode is the red cat. So that means the reduction occurs in the cathode. Very important that. Now, let's write the half reactions of these half cells. So it's going to be zinc. Since it's oxidizing, it's a zinc atom. It oxidizes to zinc 2 plus 2 electrons, right? And then, goodness. Okay, let's leave it like that. Okay, so I'm going to have here the copper, it's Cu 2 plus. Where did we get this? We get it from the table, Cu 2 plus, right? And another thing, guys, here, the anode, it loses the electrons, so the electron will move from an anode to a cathode. As I've mentioned, the electrons, they move from anode to cathode. So those electrons will move in that direction, right? The electrons will move in that direction. So what's going to happen as it loses the electrons, the zinc, it's going to become positively charged. It's going to become positively charged. As it becomes positively charged, the zinc ions will move to the electrolyte. The zinc ion will move to the electrolyte, So this electrolyte will be full of zinc electrolyte. So in other words, this cell, this electrode, it's going to corrode, so which means it's going to lose its pieces, it loses its mass, right? It's going to lose its mass there. So meaning that this electrolyte, this is an electrolyte, guys. You must know the definition of an electrolyte. An electrolyte is a solution that conducts electricity. So this electrolyte is made up of zinc sulfate. Zinc sulfate is a soluble salt, which is, there will be zinc ions and sulfate ions. There are a lot of them. They were balanced. Before this loses the electrons, there were positives and negatives that are balanced there. So it was a balanced charges. There were balanced ions here. The ions were balanced here. The number of zinc ions and the copper and the sulfate ions were balanced there. And if this is in standard condition, that means the concentration of this electrolyte will be 1 dm3, right? And its temperature will be 25 degrees Celsius or 298 Kelvin, right? So, so what is happening here? So this will become positively charged because the positive are moving. This zinc, it's breaking or it's corroding. It's corroding. So the pieces of zinc are going in the solution, down there. I'll show you the simulation of this. So what is happening there? So this will become positive. There will be a lot of zinc. It will be positively charged, right? So we say by that, in the anode, there's a mass decrease. There is a mass decrease because this electrode will corrode and will lose its mass. This electrode will lose its mass, right? And then, since there will be an imbalance here, there will be an imbalance of charges because the protons there will be greater than the electrons. So if the protons are greater than the electrons there, the salt bridge will need to rescue that. In the salt bridge, there's an insoluble salt there, the potassium chloride. There are potassium ions that are there, and there are potassium ions that are there, and there are chloride ions, a lot of them that are there. So what's going to happen? Since this is more positive according to Le Chatelier's principle, so the system needs to oppose that. The N ions will go, which is the negative, will go through the salt bridge and be added there and balance the charges. So in the salt bridge, the N ions go to the anode, right? And then as this anode loses electrons and this copper, it's gaining electrons. So gaining electrons, it makes this to be negatively charged. So as it negatively charged, there's an electrolyte here. This electrolyte is made up of copper sulfate. Since there's a copper electrode, so there are a lot of copper 2 plus that are there. The copper 2 plus, which is the Cu2 plus, there are a lot of them with the sulfate ions as well. Sulfate, it acts as a spectator there. So what is going to happen then? These copper ions there, since the electrode, the copper electrode, which is this electrode, become negatively charged, it's the copper ions, since are positives, they will be attracted there. They will be attracted there, so they will be attracted there and be reduced there. They will be reduced there. They will be attracted there. So they will form a solid. Do you see? The Cu2 plus will be attracted there and be reduced and gain electrons and become solid. So here's the solid. There's a solid that is deposited here. So now we conclude that In the anode, there is a mass, in the cathode, sorry, there is a mass increase here. There is a mass increase there. So as the copper ions are leaving the electrolyte, the copper ions are leaving the electrolyte, are going to that electrode, are attracted there. So there will be less positives here, and the sulfate will be more. So this electrolyte will be negative. So what do I mean? The electrons will be more than the protons that are there, which is the positives. The negatives will be greater than the positives. So there will be an imbalance of ions there. So the salt bridge need to maintain that electrical neutrality, as its function states that it maintains the electrical neutrality. So the cation ions will go there, right? A lot of cation ions in the salt bridge will go there. So the cation ions will go to the what? To the cathode. It's very important to memorize that, right? So guys, I think by that I've just explained, I've summarized there. I've summarized the galvanic in a nutshell. So in the external circuit, the electrons move in one direction, and then internally the ions move in two directions. The N ions move to the anode, the cation ions move to the cathode, right? In these two half cells, guys, these two half cells, we can write what we call, say, that is a net cell, which is balancing. I'm balancing that. So if you look at the electrons there are two electrons that the copper is going to receive and two electrons that the zinc is losing. So when you write the net cell, you start with the reactants. In the reactants, you have the zinc. In the reactant there, you have copper ions. So I'll say zinc plus copper 2 plus, and then arrow. And then these two electrons, since they are balanced, this 2 is 2, they will be cancelled. And then now we go to the product. The product, the zinc Zn2 plus, and the product is that. So I'll say Zn2 plus, and then plus Cu. There's no need to write states, guys, there. The aqua and the solid, you get full marks without that. So guys, I hope that makes sense. Now let's look at the cell notation. There's something that is called cell notation. The cell notation, it's symbolized, or it shows what is happening in the galvanic cell. It's a summary of what is happening in the galvanic cell. So the cell notation here, it's going to be its anode and the salt bridge and the cathode. Guys, always the anode will be on the left and the cathode will be in the right. But here, the anode can be in this side and the cathode can be in this side. So in any side. But when you write it like this, you start with an anode and then the cathode. And then, guys, this is just the summary. So what are we doing? What are we doing? Now, the anode, what is our, now how do we write the cell notation? You start with the reducing agent and then the state chain, and then after writing the reducing agent, you write the reactant of the reducing agent. Guys, this is not how you write this, but this is just the general way to write this. This is what I'm showing you, that it's very important to note that, guys. This is not how you write it. I'm just showing you the general way of writing that. So guys, it's a reducing agent, and then it's going to be a product of an oxidation. Product of oxidation. Like product of oxidation. What do I mean by that? What do I mean about the product of oxidation? The product of oxidation, guys, here, Okay, let me just write it, and then I'll show you when I write an actual cell notation of that, right? I'll show you when I do that. So, and then it's a cell bridge, and then here it's going to be a product. The next thing, it's going to be a product of, no, it's not going to be a product, it's going to be an oxidizing agent, and then the product of reduction, right? So what are we doing here? I will say, what is the reducing agent? The reducing agent is in the oxidizing agent. It's in the oxidation, sorry. The reducing agent is this, so it's going to be zinc, and then the state chain, and then it says here the product of oxidation. That's the product, is going to be Zn2 plus, and then the soul bridge, and then what it says now, it says the oxidizing agent. What is an oxidizing agent? The oxidizing agent, we get it in the reduction, which is this. So it's going to be what? Cu2 plus, and then it says the product of reduction. The product of reduction, here's the reduction. The product of reduction is that one. The state chain is going to be Cu. So that's the cell notation, guys. That's how you write the cell notation. And it is a calculation. The EMF, or the E cell, the initial cell, right? The calculation of that, guys, you use the formula that says E cell. You get it in the data sheet. It says E theta cathode minus E theta anode, right? Guys, this is the one of the formulas. This is the easiest, and make sure, guys, you write cathode there and not cat, and then here N, it's full cathode and full anode, right? So when calculating for the above cell, the cathode, it was the copper. The voltage for copper is 0.34. It's 0.34 positive, and then minus, and that minus, and then an anode, which is for zinc. For zinc, it's negative 0.76. Negative 0.76. And then when you punch that in the calculator, it's going to be adding the two, it's going to be 1.1 volts. That's the voltage that is induced when the two. Now let's look at the equilibrium. What do we mean about the equilibrium? The equilibrium in the galvanic solution, right? We know what do we mean by equilibrium. The equilibrium, it means the rate of forward is equal to the rate of reverse. Here in this case, we say the rate of oxidation is equal to the rate of reduction. So the rate in which the electrons are lost is the rate in which the electrons are gained. So when the galvanic cell, or the cell, is at equilibrium, it means that the cell has run flat. So what do we mean by the cell has run flat? That means the battery is flat. Battery is flat. That means the voltage, or the EMF now, or the E cell, it has decreased to 0, right? So whenever they ask you why is the cell is 0, it means it has reached equilibrium, right? It has reached equilibrium. What does it mean it has reached equilibrium? It means the rate of reduction is equal to the rate of oxidation. When the cell runs flat, or the battery is flat, that means the voltage that is induced there, the EMF or the E cell, is 0 because of equilibrium, right? Now let's look at how does the change in concentration, How does the change in concentration affect? Let's look at the change in concentration affect where the change in concentration of what? Of electrolytes. So in those electrolytes above, if you change, it affects the EMF, right? Or the E cell. How does it affect the E cell? Now, very important, to answer that question, you need the net cell, right? The net cell is very important here in explaining or in your argument or in answering the question of the EMF. Let's say here, if we add the concentration of Cu2 plus, let's say now in this case, we're adding the concentration of zinc in the solution, meaning in this electrolyte we are adding the concentration of zinc, right? Adding the concentration of zinc. Now, where is the zinc ion? It's in the product. That means the change that I'm doing, it's in the product. So I'm adding, which is I'm increasing the concentration. That's the disturbance that I've done in the system. So according to Le Chatelier's principle, the system is going to oppose the change and decrease that. So what does it decrease? It decreased zinc, which is the zinc, it's in the product. That means that the product, which is the forward, is not favored. So what is the system is going to do is going to increase the reactant. That means the reverse is favored. So here, reverse is favored. So once the reverse is favored, that means that the E cell or the EMF is going to what? Decreases all the time in the change of the concentration. Whatever that you have done in the concentration, if it favors reverse, that means the E cell decreases. When reverse is favored, that means decreases. The EMF will decrease, which is this EMF, the voltage reading here will decrease. Okay, now let's look at when we remove the concentration of copper 2 plus. Let's say we decrease the copper of 2 plus, of Zn 2 plus, of copper ions. We decrease the concentration of copper ions. I need this again. Here is it. So what did we do? What is our disturbance? We remove. That means we decrease the concentration. This is the disturbance. According to Le Chatelier's principle, the system is going to increase it, right? The system is going to increase it and increase that. What is going to do in the product? Decrease the product, decrease the product. So that means here, the forward is not favored, the reverse is favored. So that means reverse is favored, right? So if reverse is favored, again, the E cell and the EMF will what? Decrease. When does the forward is favored? The forward is favored when the system responding by increasing the product, right? In whatever change that is happening here, let me do it for the last time. Where forward is going to be what? Forward is going to be increased. So if forward is favored, now let's do this now. Let's say we remove the concentration of Zn2 plus, which is the zinc ions in the electrolyte. We are decreasing the concentration. The square bracket is the concentration, guys. So what are we doing? as the Zn2 plus, we're disturbing the system by decreasing the decreasing the zinc ion. So what is the system going to do? Is going to oppose that and increase it and increase the product, and then the reactant is going to decrease them. So that means the reverse is not favored, the forward is favored. So if a forward is favored, if forward is favored, that means the E cell or the EMF is going to what? Increases. So all the time, guys, if forward is favored, the E cell has increased. Right? Right. Okay, guys. Now let's look at the mass change calculation. In the calculation, when you calculate the mass change calculations, which is this one, guys, is the stoichiometry, right? So our net cell, it was Zn Cu2 plus, and then Zn2 plus and Cu, right? So guys, let's go back a bit above. So let's look here. The zinc here, the mass was decreasing. From the original mass, it was decreasing. So if we're given the amount that it has decreased by, that means if it has decreased by the certain amount here, also here there will be an increase in mass by a certain amount, but it doesn't mean it's going to be the same, guys. If it decreases by 2 grams here, it's going to increase by 2 grams there. It doesn't mean that. But if we're just given the amount that is going to decrease by there, so it can help us to calculate the amount that the cathode is going to increase by. So now what are we going to do? Let's say in a case we are told that the zinc as an anode, let's say in a case where we are told the zinc as an anode, it decreases by 3.2 grams, right? It decreases by 3.2 grams. Okay, let's say, let us not say 3.2 grams. Let's just say use a smaller value. Let's say the value is 0.6 gram. That mass of an anode in the zinc, it decreases. So this is the mass decrease of what? Of zinc. So now we want the mass increase of that, right? That's what we want. So what are we going to do? Step number 1, I'm going to convert the mass change of zinc to the number of moles of zinc, right? And then step number 2, this number of moles of zinc, I'm going to, okay, step number 2, I'm going to do the mole ratio. The mole ratio, keep finding which is changing the number of moles that I've changed above in step number 1 of zinc to the number of moles of what? Of copper. So now, having the number of moles of copper, I will change the number of moles of copper into the mass of copper. That means I know the mass change of copper. Now let's do step 1. Step number 1. So I'm going to calculate the number of moles of zinc using this formula, which is going to be the mass, it's 0.6. The mass is 0.6, and the 0.6 we divide by the molar mass of zinc. The molar mass of zinc, it's 65.4, and then when you divide that, you get 0.0092 mole. And then step number 2, which is we're done with step number 1, and then we'll do the mole ratio. So the mole ratio, I'll say zinc is to copper. What is the mole ratio? The mole ratio in that is 1:1. So the ratio is 1:1. That means it's going to, the number of moles are going to be the same, right? Number of moles are going to be the same. So if the number of moles are the same, that means the number of moles of copper, it's 0.092 mole. Right? Step number 3. In step number 3, we're going to change this number of moles into the mass, and then we are done. So the number of moles is equal to the mass of the molar mass of that. So the number of moles is that 0.092, and the mass, that's the one we want, and the molar mass of copper is 63.5, and then if you cross multiply the mass of copper, which is going to be 0.58. So this is the mass increase of copper in the cathode, right? Graphically, guys, it's going to be time here in seconds, and it's going to be mass here in grams. So what is happening here? The anode, there's a mass decrease. Let's say its mass, it started there, and then it decreases there, and then the cathode, its mass doesn't start from 0, it starts there. There will be a mass increases. So here guys, it's at equilibrium. Okay, this, let's say this is a cathode, and this is an anode. This is at equilibrium, guys. Equilibrium, it's when the cell has equilibrium, it's when the cell is flat, right? And guys, I hope you understand this and it makes sense. Cheers, bye.